Okay, this is Ben Winokur's Kitchen Science Final. Today I'm going to talk about emulsions, and I'm also going to talk about the lipids involved in the emulsions. In this case, we're using olive oil. Okay, so this is the structure of oleic acid triglyceride, which is the main triglyceride found in olive oil. It's usually around 70% of the triglycerides involved in olive oil. So if we look at this structure, we have the glycerol backbone, the 3 carbons connected to oxygens, and there's implied hydrogens at all of these corners there. It's just easier to draw that way. So the glycerol backbone, it's got 3 carbons. They're all connected to these oxygen and the carbonyl group. And then this right here over is oleic acid. It's sometimes found in free acid form. Usually it's found in a triglyceride form. So as you can see, there are these long hydrophobic chains. It's all carbon, hydrogen, carbon, carbon, single bonds, and carbon, carbon, double bonds. This is very hydrophobic. It's nonpolar. It doesn't attract water. This is going to generally stay with itself and not associate with water when given the chance. Oleic acid in particular has a cis bond right here at the omega 7 position. So that's counting backwards from the end. It's the 7th carbon. And this is a cis bond, which is important because it makes it so oleic acid, when they're in their natural state, all these bonds can flip-flop all around, and the single bonds can spin at 360 degrees. Double bonds, if you think about 2 bonds, they can't spin around as much, not nearly as much. So they can either be in a cis formation or a trans conformation like down here. The cis conformation makes it so they can't stack next to each other. It spreads out the molecule, and this is important because it makes it so olive oil isn't a solid at room temperature. It's a liquid, and if some of these were trans, or if they were all single bonds, this would probably be a solid at room temperature. So the effect of this all being hydrophobic is when you mix, this is water in here, when you mix water and olive oil, they don't mix. The olive oil just sits on top because it's less dense, and there's no water down here, and there's no olive oil down here, and there's no water up here. So in an emulsion, you try to make this all one liquid. And in this case, we're trying to make a oil and water emulsion using olive oil and vinegar. So in this emulsion, the vinegar will be the water. It's very similar to water. It's a polar liquid. Acetic acid is a polar liquid. So we want little bits of this olive oil all dispersed throughout the continuous phase of the acetic acid. And in these bowls, I'm going to mix acetic acid, vinegar, with a little bit of olive oil. I'm going to whisk it in with my fork because I don't have a whisk, and then I will show you the results. In this one, I'm going to do the same thing, but I'm going to add mustard, an emulsifying agent, and that's going to help stabilize it and hopefully keep the emulsion in phase longer. So I will come back to that after I finish that. Alright, and here we're back. So this is just the oil and the water. This is the oil and water that I whisked together and emulsified. It's already separating a little bit in the 30 seconds it took me to turn this camera on. But you can see, if you look down, there is, oil is surrounded by the little drops of water. I don't know how well you can tell. So the point of an emulsion is to get this into one phase, and with the help of an emulsifier, in this case mustard, you can see that this is much more uniform. The bubbles in this one are much smaller, the little droplets of oil, and that's because the proteins in the mustard associate with both the oil and the vinegar, because they have a hydrophobic part and a hydrophilic part, and so by associating with the droplets of oil, it helps keep them in phase, in the dispersed into the continuous phase. And it also makes it more viscous just by adding something else in there, and that makes it more difficult for the oil to separate from the water. So that's a lesson on lipids and emulsions.